Hello and welcome dear students. Today we are going to discuss an important topic, that is major features of the ocean floor. In this lecture we will learn about the stunning complex geography of the ocean floor, a landscape far more rugged and dramatic than most imagine. Often described as Earth's last great frontier, the seabed is not a flat plain. It is a hidden world of colossal mountain ranges, deep canyons, vast abyssal plains that rival or exceed features found on the land. We will explore how scientists use bathymetry to chart this submerged topography and then dive into major features that define it. From the shallow resource-rich continental shelves to the plunging oceans, trenches home to the deepest point on the earth, and the immense volcanically active mid-ocean ridge systems that stretch across the entire globe. Understanding these features is key to unlocking the secrets of plate tectonics and the dynamic history of our planet. Seas and oceans are stunning blue beauties of Earth, making up the vast interconnected world ocean. They fill the planet's deepest depressions and dominate the hydrosphere, holding over 97% of all water. They cover an area of approximately 361 million square kilometers. Beneath the surface, the ocean floor is not flat. It is a landscape of diverse relief features. For centuries, most scientists believed the seabed is an entirely flat, featureless plain. However, mapping for things like transoceanic cables and research trips showed a hidden world beneath the ocean, a rugged landscape with deep valleys, ancient volcanoes, and massive mountain ranges that are bigger than anything on land. This module aims to introduce students the basic concepts and the major relief features of the ocean floor, helping them to understand how to measure the depth of the ocean floor, types of landforms, and their significance in oceanography. Now, oceans on Earth. A world map clearly shows the vast extent of the oceans. Most of the Earth's surface is covered by seawater, and anyone who has crossed an ocean by ship or flown over it by aeroplane is impressed by its immense size. All the seas and oceans are interconnected, forming one continuous body of seawater. For this reason, they are often referred to collectively as the world ocean. A ship at sea can move from one ocean to another without crossing land, whereas traveling between most continents and land requires crossing an ocean. The oceans contain nearly about 97.2% of all the water on or near Earth's surface, forming an enormous water reservoir. Although it is one continuous body of water, the world ocean is commonly divided into four major oceans. Number one ocean, Pacific Ocean. The Pacific Ocean is the world's largest ocean, covering more than half of the Earth's ocean surface area. The Pacific Ocean is the single largest geographic feature on the planet, spanning more than one-third of the Earth's entire surface. The Pacific Ocean is so large that all the continents could fit into the space occupied it with room left over. Although the Pacific Ocean is also the deepest in the world, it contains many small tropical islands. The next ocean is the Atlantic Ocean. Atlantic Ocean is about half the size of the Pacific Ocean and is not quite as deep. It separates the old world, Europe, Asia and Africa from the new world, North and South America. The Atlantic Ocean was named after Atlas, who was one of the Titans in Greek mythology. The Mid-Atlantic Ridge is a significant geological feature located along the floor of the Atlantic Ocean. It is a mid-oceanic ridge, which means it represents a divergent or a constructive plate boundary. This underwater structure is notably for being a part of the longest mountain ranges in the world. Now, the third one is the Indian Ocean. The Indian Ocean is slightly smaller than the Atlantic Ocean and has about the same average depth. It is mostly in the southern hemisphere, south of the equator or below 0 degrees latitude. The Indian Ocean was named for its proximity to the subcontinent of India. Number 4th ocean is the Arctic Ocean. The Arctic Ocean is about 7% the size of the Pacific Ocean and is only a little more than 1/4 as deep of the rest of the oceans. Although it has a permanent layer of sea ice at the surface, the ice is only a few meters thick. The Arctic Ocean was named after its location in the Arctic region, which exists beneath the northern constellation Ursa Major, otherwise known as the Big Dipper or the Bear. Southern Ocean or Antarctic Ocean. Oceanographers recognize an additional ocean near the continent of Antarctica in the southern hemisphere, defined by the melting of currents near Antarctica called the Antarctic Convergence. The Southern Ocean, also known as the Antarctic Ocean, is actually the portion of the Pacific, Atlantic and the Indian Ocean, south of approximately 50 degrees south latitude. This ocean was named for its location in the southern hemisphere. Now coming to the another important topic, bathymetry, mapping the hidden sea floor. This section introduces bathymetry, which is the specialized study and mapping of the depth and shape of the ocean floor. Essentially, bathymetry reveals how deep the ocean is and provides a detailed view of the seafloor features such as mountains, valleys, plains. It is the underwater equivalent of topographic mapping conducted on land. Understanding bathymetry is crucial for studying the major features of the ocean floor because it uncovers these hidden structures. Since most of the seafloor remains out of sight, bathymetry is the only way to physically identify and outline major geological features like the global mid-oceanic ridge system and deep sea trenches. Each major feature of the ocean floor is characterized by its distinct depth and shape, which are measured through bathymetry. For instance, the continental slope is characterized by steep bathymetric gradient, whereas the abyssal plain is recognized by its extremely flatness at great depth. Bathymetry relies on measurements of water depth, traditionally called soundings. Many soundings are combined to construct detailed maps of the sea floor. These bathymetric maps commonly use two key tools for visual representation. The first one is color scales. Different colors are used to visually represent different depths, immediately highlighting shallow areas versus deep trenches. Depth contours are also commonly known as isobaths. These are lines that join points of equal depth, similar to how contour lines are used to show elevation on land maps. Techniques used to determine the ocean bathymetry. Bathymetry is measured by finding the vertical distance from the sea surface down to the sea floor. Two main methods are traditional sounding and echo sounding. Now, the sounding or the lead line method. The earliest depth measurement soundings were made using a rope or a wire with a weight attached. The line was lowered until the weight touched the bottom and the length of the line gave the depth. The standard unit of the ocean depth is known as the fathom, equal to 1.8 meters or we can say around some 6 feet. The first systematic scientific depth measurements were made during the voyage of HMS Challenger during the 1870 to 1876. The crew periodically measured depth along with other ocean properties. These data showed that the deep ocean floor is not flat but has a significant relief similar to land. However, lead line soundings are slow and sparse, so they cannot give a detailed picture of the sea floor. The another method is that is known as echo sounding method. Modern bathymetry mainly uses echo sounding fathometer. An echo sounder sounds a sound pulse pinch from a ship down to the water. The sound reflects echoes from the seafloor and returns it to the ship. Because sound travels at the known speed in a seawater, the time taken for the echo to return can be used to calculate depth and map the shape of the sea floor. In the 1920s, for example, a German ship Meteor used echo sounding to discover a long underwater mountain range in the South Atlantic Ocean. Echo sounding revealed that the sea floor has ridges, trenches, seamounts, and other features. What does the Earth's hyposophographic curve show? A hyposophographic curve shows how Earth's surface area is distributed with height on land and depth in the oceans. From the hyposophographic curve, we learn more than 70% of Earth's surface is covered by oceans. The average ocean depth is around 3,729 meters. The average land elevation is about 840 meters. Coming to our main topic, that is the features of the ocean floor. Beneath the seemingly flat ocean surface lies a dramatic, complex underwater landscape. This ocean floor is remarkably rugged, featuring the planet's largest mountain ranges, deepest trenches, and most extensive plains. These submarine landforms, collectively known as ocean relief, are not random. They are primarily the result of the same powerful geological forces that shape the continents, known as the movement of plates, volcanic activity, erosion, and deposition. While the ocean has an average depth of 3,700 meters, the actual shape of the sea floor is incredibly varied, created by continuous interactions of these processes. The vast and the varied landscape of the ocean floor, known as ocean relief, is broadly categorized into two types based on the scale and formation. Major ocean relief features are the primary ones, large-scale divisions of the seafloor. These include the continental shelves, the continental slopes, the continental rises, deep sea abyssal plains, which together form the foundational structure of the ocean basins. The next ones are the minor ocean relief features, smaller landforms superimposed on the major divisions, such as mid-oceanic ridges, seamounts, goyets, deep sea trenches, submarine canyons, and coral reefs. Now, first we will discuss the continental shelf. The continental shelf is defined as a generally flat zone extending from the shore beneath the ocean surface to the point at which a marked increase in slope angles occurs, called the shelf break. It is usually flat and relatively featureless because of marine sediment deposits, but can contain coastal island reefs and razor banks. The underlying rock is granitic continental crust, so the continental shelf is geologically part of the continent. The general bathymetry of the continental shelf can usually be predicted by examining the topography of the adjacent land. The average width of the continental shelf is about 70 kilometers, but it varies from few tens of meters to 1500 kilometers. The broadest shelves occur off the northern coasts of Siberia and North America in the Arctic Ocean. The average depth at which the shelf break occurs is about 135 meters around the continent of Antarctica. However, the shelf break occurs at 350 meters. The average slope of the continental shelf is only about a tenth of a degree, which is similar to the slope given to a large parking lot of drainage purposes. The type of continental margin will determine the shape and the features associated with the continental shelf. For example, the east coast of South America has a broader continental shelf than its west coast. The east coast is a passive margin, which typically has a wider shelf in contrast to the convergent active margin present along the west coast of the South America. It is characterized by a narrow continental shelf and a shelf break close to the shore. The continental shelf of the west coast of India, especially near the Mumbai in the central Arabia Sea, is quite wide. You can say around some 300 kilometers. To the east, there is also a shelf along the Bay of Bengal, the Bengal shelf, but it is generally narrower than the Arabian Sea shelf. The next important major feature is the continental slope. The continental slope, which lies beyond the shelf break, is where the deep ocean basins begins. Total relief in this region is similar to that found in mountain ranges on the continents. The break at the top of the slope may be from 1 to 5 kilometers above the deep ocean basins at its base. Along convergent active margins, where the slope descends into submarine trenches, even greater vertical relief is measured. Off the west coast of South America, for instance, the total relief from the top of the Andes Mountains to the top of the Peru Child Trench is about 15 kilometers. Worldwide, the slope of the continental slopes converges about 4 degrees but varies from 1 to 25 degrees. Of the eastern coast of India and Bangladesh, the continental slope forms the edge of the Bay of Bengal basin, dropping down towards the deep floor where the Bengal fan lies. On the Arabian side, the slope edges the western continental shelf of India, while the average steepness is deceptively gentle 4 degrees. This is a global mean. In reality, the slope angle is highly variable on passive margins like the east coast of the America. Slopes are typically gentler. On active margins like the Pacific Ring of Fire, which we commonly known as, slopes are much steeper, often exceeding 10 degrees and can be as sharp as 25 degrees in some sections, forming near vertical wall. The third is the continental rise. The continental rise is a transition zone between the continental margin and the deep sea ocean floor, made up of a large submerged pile of debris. Where did all this debris originate and how did it arrive there? The presence of turbidite currents indicates that the material transported by these currents is responsible for forming continental rises. When a turbidity current flows through and erodes a submarine canyon, it exits at the canyon's mouth. The slope angle decreases and the turbidity current slows down, causing suspended material to settle in a distinctive type of layering called as graded bedding, which grades in size upward. As the energy of the turbidity current weakens, larger particles settle first, followed by progressively smaller ones, until very fine particles settle out, which can happen weeks or months later. A single turbidity current creates a graded bedding sequence. The next turbidity current may partially erode the previous deposits before forming another graded bedding layer on top. Over time, this process can produce a thick sequence of graded bedding layers. These stacks, known as turbidite deposits, which make up the continental rise. From above the deposits at submarine canyon, mouths appear fan-shaped, lobate or apron-like. As a result, these deposits are called deep sea fans or submarine fans. Deep sea fans form the continental rise where they converge along the base of the continental slope. In contrast, along the convergent active margins, the steep continental slope directly leads into deep ocean trench. Sediment from turbidity currents accumulates in the trench, preventing the formation of a continental rise. One of the largest deep sea fans globally is the Indus fan, a passive margin fan that extends 1800 kilometers. The Bengal fan in the Bay of Bengal and the Indus fan in the Arabian Sea are huge sediment fans fed by the Ganga, Brahmaputra and Indus rivers. They form the continental rise and then grade into the deep basins. Next comes the abyssal plains. Extending from the base of the continental rise into the deep ocean basins are flat depositional surfaces with slopes of less than a fraction of a degree that cover extensive portions of deep ocean basins. These abyssals, which actually means without basis means bottom, plains average between 4,500 meters to around 6,000 meters. They are not literally bottomless, but they are some of the deepest and the flattest regions on the earth. Abyssal plains are formed by a fine particles of sediment slowly drifting onto the deep ocean floor. Over millions of years, thick blanket of sediment is produced by suspension settling as fine particles. Analogues to marine dust accumulate on the ocean floor. Few abyssal plains are located in the Pacific Ocean. Instead, most occur in the Atlantic and Indian Ocean. The deep ocean trenches found on the convergent active margins of the Pacific Ocean prevent sediment from moving past the continental slope. In essence, the trenches act like a gutter that traps the sediment transported off the land by turbidity currents. On the passive margins of the Atlantic and the Indian Ocean, however, turbidity currents travel directly down to the continental margin and deposit sediments on the abyssal plains. In addition, the distance from the continental margin to the floor of the deep ocean basins in the Pacific Ocean is so great that most of the suspended sediment settles out before it reaches these distant regions. Conversely, the smaller size of the Atlantic and Indian Ocean does not prevent suspended sediment from reaching their deep ocean basins. The deep ocean floor of the central Indian Basin south of India, which is a part of Indian Ocean abyssal plain system, is a good regional example. Another one are the volcanic peaks of the abyssal plains. Poking through the sediment cover of the abyssal plains are a variety of volcanic peaks, which extend to various elevations above the ocean floor. Some extend above the sea level to form islands, while others are just below the surface. Those that are below the sea level but rise more than 1 kilometer above the deep ocean floor and have a pointy top like an upside down ice cream cone are called as seamounts. On the other hand, if a volcano has a flattened top, it is called as a table mount or guyot. Volcanic features on the ocean floor that are less than 1000 meters tall, the minimum height of the seamount is called abyssal hills or scenic knolls. Abyssal hills are one of the most abundant features on the planet and cover a large percentage of the entire ocean basin floor. Several seamounts and ridges in the Indian Ocean have recently been named, such as Ashoka Seamount, Chandragupta Ridge and Kalapatura Ridge along the southwest Indian Ridge, discovered and named by the Indian institutions. Oceanic trenches and volcanic arcs. Oceanic trenches are deep linear scars in the ocean floor caused by the collision of two plates along convergent plate margins. The landward side of the trench rises as a volcanic arc that may produce islands, such as the islands of Japan, an island arc, or a volcanic mountain range along the margin of the continent, such as the Andes mountain is a continental arc. The deepest portion of the world's oceans are found in these trenches. In fact, the deepest point of the Earth's surface, which is around 11,022 meters, is found in the Challenger Deep area of the Mariana Trench. The majority of the ocean trenches found along the margins of the Pacific Oceans, while only few exist in Atlantic and Indian Oceans. The Pacific Ring of Fire, which occurs along the margins of the Pacific Ocean. It has a majority of the Earth's active volcanoes and large earthquakes because of the prevalence of convergent plate boundaries along the Pacific Rim. What features exist along the mid-oceanic ridges? The global mid-oceanic ridge is a continuous fractured looking mountain ridge that extends through all the ocean basins. The portion of the mid-oceanic ridge found in the North Atlantic Ocean is called as the Mid-Atlantic Ridge, which dwarfs all mountain ranges on land. The enormous mid-oceanic ridge forms Earth's longest mountain chain, extending across some 75,000 kilometers of the deep ocean basin. The width of the mid-ocean ridge averages about 1000 kilometers. The mid-ocean ridge is topographically high feature, extending an average of around 2.5 kilometers above the surrounding sea floor. The mid-ocean ridge contains only a few scattered islands such as Iceland and the Azores, where it peaks above sea level. The mid-ocean ridge is entirely volcanic and is composed of basaltic lavas characterized by the oceanic crust. Along most of its crust is a central down-dropped rift valley created by seafloor spreading where two plates diverged. Along the mid-Atlantic ridge, for example, is a central rift valley that is as much as 30 kilometers wide and 3 kilometers deep. Here, molten rock presses upward toward the seafloor, setting off earthquakes, creating jets of superheated seawater and eventually solidifying to form a new oceanic crust. Cracks and fissures and faults are commonly observed in the central rift valley. Swarms of small earthquakes occur along the central rift valley, caused by the injection of magma into the seafloor or rifting along faults. Segments of the mid-ocean ridge, called as oceanic ridges, have a prominent rift valley and steep rugged slopes, and oceanic rises have slopes that are gentler and less rugged. Now let us see the volcanic features. Volcanic features associated with the mid-oceanic ridges include tall volcanoes called seamounts and recent underwater lava flows. When hot basaltic lava spills onto the seafloor, it is exposed to cold seawater and chills the margins of the lava. This creates a pillow lava or a pillow basalt, which are smooth, rounded lobes of rock that resemble a stack of bed pillows. Frequent volcanic activity is common along the mid-oceanic ridge, that is hydrothermal vents. Other features in the central rift valley include the hydrothermal vents. Hydrothermal vents are seafloor hot springs created when cold seawater seeps down along the cracks and fractures in the ocean crust and approaches an underground magma chamber. The water picks up heat and dissolved substances and then works its way back towards the surface through a complex plumbing system, exiting through the sea floor. The temperature of the water that rushes out of a particular hydrothermal vent determines its appearance. These are warm water vents. These are having water temperature below 30 degree and generally emit water that is clear in color. White smokers have water temperatures around 30 to 350 degrees centigrade and emit water that is white because of the presence of various light colored compounds including barium sulfide. The another ones are the black smokers. Black smokers have water temperatures around 350 degrees centigrade and emit water that is black because of the presence of dark colored metal sulfides including rock, nickel, copper and zinc. Another interesting features are the oceanic islands. Some of the most interesting features of the ocean basins are islands, which are unusually tall features that reach from the sea floor all above to the sea level. There are three basic types of oceanic islands. Number one, the oceanic islands associated with the volcanic activity along the mid-oceanic ridges, such as the Ascension Island along the mid-Atlantic ridge. The other ones include the islands associated with the hotspots, such as the Hawaiian Islands in the Pacific Ocean. And the third ones are the islands that are the island arcs and associated with the convergent plate boundaries. These include the Aleutian Islands in the Pacific Ocean. Note that all three types of volcanic in origin. In addition, there is a fourth type of an island that are parts of continents, such as the British Isles of Europe. But these occur close to shore and thus do not occur in the deep oceans. Dear students, this was all about today's program. Hope you enjoyed it well. Thank you for watching.